Okay, so up to now, what have we been doing? We've been working with bodies, right? And all the bodies we've been working with have been point particles, or point masses. Everything has been a point mass. That's why when we draw our free body diagram, we just draw a little circle and put the forces on it. We don't worry about the size or the extent and all those properties. We don't worry about the orientation. But now we're going to get more realistic, or more real, as your generation would say. More real, we're going to work with, and this is the technical term, rigid bodies. All right, so what does rigid bodies mean? It means they have size and shape and direction. Not direction in the career sense, but direction means they point a specific direction. Okay, a direction in space around an axis. Okay? So that's what happens when something gets big. A point particle, you can't really say which direction it's facing. And you can't really say what its shape and size is. It doesn't have anything. It's just a point particle. But as soon as we let it be something big, suddenly it can have size, shape, and direction. We can get even more real and go to the next level. Next week is deformable bodies. Oh, that's definitely more real for me. Deformable bodies mean things like elastic that you can stretch and expand. That's next week. We're going to spend like half a lecture on it. It's really not that important for this class. We're mostly talking about things that always maintain their shape. Do you want to get even more real? I saw lots of no's. Okay, so even. I-V-I-E, look it up, okay? Even more real is reconfigurable bodies. So you may have had a moment in high school where you asked your high school physics teacher, how is it they were able to walk? How does that work? Or why can a car go forward just using static friction? What? That doesn't make any sense. And that's because you have to go to reconfigurable bodies to be able to explain that. You have to have something that can take one part of its body and put it here, and then take this part that was behind that part and put it over here. And then this part was behind that part and put it over here. Right? That's why something can walk. You can't really explain it with this, or this, or this. Right? You have to go all the way to basically kinesiology. All right? So that's why we don't do lots of examples about walking and driving cars, because it's just confusing. All right? So here we go. Let's think about, I forgot my little pendulum. So if we imagine we have a pendulum, so the way we would have thought about a little mass on a string before, I think about the big mass that was going in a circle, our physical pendulum. It went back and forth, and we didn't really think about what was really happening with the bowling ball, did we? But if we had looked at the little 3 fingers, wait, how many fingers are on both? 3? 3. If we had looked at the little 3 fingers, they would have been tilting down here, and then when it got up to here, they would have been kind of tilting up here. Right? The bowling ball was actually rotating because it's a real ball. It's not a point particle. So when we did all of our analysis, we said, oh, it's just a point mass. Let's just draw its free body diagram like this, mg down and tension up, and we went to town. Okay? But in reality, everything actually has orientation that you have to think about. It is possible to move a bowling ball in a way where it doesn't change its orientation. You could do it. But just the way things naturally move, they tend to change their orientation, which is why we have to talk about it in physics, right? That's what rotational motion is. Okay? So that's what we're doing. All right. Here we go. Here we go.